In this session, let us solve a numerical problem on the automatic generation control of two-area system. First of all, let me explain the backdrop of this problem. Now we consider two single area system. Let this one be area 1. This is area 2. Each single area represents one generating stations with a set of loads. So the first area may be represented by one power plant, the Ramagundam thermal power plant, which is in Andhra Pradesh. This is our first single area. Suppose the second single area is another power plant. We consider the Neyveli power plant. So Neyveli thermal power plant, which is in Tamil Nadu. Suppose these two single areas or these two generating stations are interconnected through a transmission line called a tie line. Now suppose we have a surplus power in the first single area system. So we are giving certain power to the second area. This is the tie line power. The power supplied to the second area through the tie line. We call it tie line power. Now we consider a heavy load connected to the first single area system. When an additional load is connected to the first single area system, let us consider what are the events taking place. Now the load demand is increased in the first area and these two areas are connected together, the frequency will reduce. This is our frequency versus power demand graph. When the power demand or the electrical load increases, the frequency drops. So in both areas, the frequency will reduce. These two areas are connected in parallel. So the frequency will be same, but this frequency will reduce. Now, the load demand on the first area is increased. So we have to meet this additional load demand. Now let us consider all possibilities to meet this additional load demand. The first possibility is we can increase the mechanical power in the first area. When you give more mechanical power, obviously the power generation in the first area will be increased, and thereby we can meet a part of the additional load demand. And the second possibility is we can reduce this tie line flow. Let us reduce the power given to the second area, because now we do not have the surplus power, because we are in need of additional power. So we cannot give the same power to the second area now. So let us reduce the tie line flow. As the power being given to the second area is reduced, but still it is having the same electrical load connected in this second area. So how can we meet the load demand in the second area? Let us increase the mechanical power in this second area. That is the only possibility left. When you increase the mechanical power, the power generation in this second area will be increased. And thereby, we can meet the demand here, the load connected in the second area. Because earlier we were being supplied from the first area. Now, the first area has stopped supplying the power to second area, as their demand is increased. Now the possibility to meet the load demand in the second area is by increasing the power generation here. How can we increase the power generation? By increasing the mechanical power given to the turbines, or by giving more amount of steam input to the turbine. So these are the events taking place when you connect an additional load in the first area. The frequency will reduce, the mechanical power in the two areas will increase, and the tie line power will be reduced. Now let us solve this numerical problem. Let us choose this 100 MVA as the common base. The nominal frequency is 60 Hertz. The synchronizing power coefficient is given. This is the change in load in the first area. We are connecting 187.5 megawatt in the first area. We have to find out the new steady state frequency, the change in tie line flow, the change in mechanical power in each area. The parameters of the two single area systems are specified. Now let us choose MVA base equals 1000 MVA. Now what is the change in load here? The change in load in the first area, delta PL1 equals 187.5 megawatt. What is the per unit change? Let me write delta PL1 per unit, or in per unit this is equal to 187.5 divided by the base MVA. The base MVA is 1000 megawatt. So this is equal to 0.1875 per unit. Let me write the value here. Delta PL1 equals 0.1875 per unit. Now let us find out the steady state frequency deviation. The steady state per unit frequency deviation. Delta omega SS. This is equal to minus delta PL1 divided by B1 plus B2. B1 and B2 are called the frequency bias factors. They are called the frequency bias factors. B1 equals 1 by R1 plus D1. What is R1 in the first area? It is 0.05, the speed regulation. So it is 1 by 0.05 plus D1 equals 0.6. So this is equal to 20.6. And B2 equals 1 by R2 plus D2. What is 1 by R2? 1 by 0.05. Sorry, R2 equals 0.0625. 0625 plus D2 equals 0.9. And this B2 equals 16.9. This is 16.9. What is the per unit change in steady state frequency? Delta omega SS equals minus delta PL1, which is minus 0.1875 divided by B1 plus B2. 20.6 plus 16.9. And this is equal to minus 0.05 per unit. This is the per unit change in frequency. Now let us find out the change in frequency in Hertz. This per unit change is same whether it is in radian per second or in Hertz. Now let us find out the change in frequency in Hertz, which is equal to the per unit change minus 0.05 into the nominal frequency, which is 60 Hertz, which is equal to minus 0.3 Hertz. So there is a change of minus 0.3 Hertz. So what is the new frequency? F new equals the old frequency, the nominal frequency plus the change. The change is minus 0.3. So which is 60 minus 0.3, which is equal to 59.7 Hertz. So this is the new system frequency after the load is connected in the first area. Now let us find out the other parameters. Before that, let me write B1 and B2 here. What is B1? 20.6. We need these parameters to solve the remaining parts of the problem. B2 equals 16.9. Now let us find out the change in tie line flow. And later we can find out the mechanical power change in two single areas. Let us find out the change in tie line flow. Delta PL1, delta P12. Let us find out the per unit change in tie line flow. Delta P12 equals minus B2 divided by B1 plus B2 into minus delta PL1. What is our B2? It is 16.9 divided by B1 plus B2. It is 20.6 plus 16.9 into the change in load is 0.1875 per unit. And this is equal to minus 0.0845 per unit. What is the actual change in power? This is the per unit change. What is the actual change? Delta P12 equals this per unit change into the base power. What is the base MVA? 1000 MVA, which is equal to minus 84.5 megawatt. So when the load is connected in the first area, or when the load in the first area is increased by 187.5 megawatt, the tie line power is reduced by 84.5. This minus sign shows the reduction in the tie line flow. The tie line flow is reduced by 84.5 megawatt. Now let us find out what are the changes in mechanical power. The per unit change in mechanical power. We are finding out the per unit change in mechanical power. Delta PM1 equals 1 by minus delta omega divided by R1. So this is equal to minus, what is the change in frequency? This is minus 0.05 per unit. Minus 0.05 per unit. We have already calculated this value. Divided by, what is R1? 0.05. So this is equal to and this part is minus 0.005 per unit. The change in frequency is minus 0.005. And this is equal to 0.1 per unit. What is actual change in load? Delta PM1 actual is equal to this per unit change into the base power, which is 1000 MVA. So it is 100 megawatt. So the change in mechanical power in the first area is 100 megawatt. So this much of additional mechanical power should be supplied to the first area in order to increase the power production, in order to increase the power generation in the first area. What is delta PM2? It is minus delta omega divided by R2, which is equal to minus 0.005 divided by R2 equals 0.0625. And this is equal to minus 0.080 per unit. What is the actual change in mechanical power in the second area? This per unit change into base power. 0.80 into the base MVA is 1000. So this is equal to 80 megawatt. So 80 megawatt is given in addition to the actual value. This is the additional increase in mechanical power in the second area. This is the additional increase in mechanical power in the first area. So these are all the events taking place when an additional load is connected in the first area. When this much of load is connected in the first area, the frequency is reduced. What is the new frequency? This is 59.7 Hertz. It is reduced from 60 Hertz. Then the tie line flow is reduced. The tie line flow has been reduced. Then the mechanical power in the two areas are increased in order to meet the additional load demand.